All right, so on Friday, we talked about rational inequalities, so we can figure out where our functions were positive or negative or zero. We're going to look at some of the discontinuities in rational functions today. So tell me what kind of discontinuities we could have. Jump, infinite, point. Okay, point and removable, same thing, good. And so your point can also be called removable discontinuity. Those are the same names. Jump discontinuity is only going to happen if you have a piecewise. Okay, so that is a discontinuity we need to know, but that's going to happen with piecewise. And then infinite means we have what? An asymptote. So your infinite discontinuity that we had talked about when we were looking at discontinuities in the domain had to do with the vertical asymptotes. But besides vertical asymptotes, what other kind of asymptotes can you have? Horizontal or slant, okay? So horizontal, slant, and vertical asymptotes. All right, so I'm going to show you a picture here of, first of all, is this graph a function? No. Fails the vertical line test, not a function, but it just has kind of everything together. It was the best one with everything that I could find on there. But you know what a horizontal asymptote looks like. You know what a vertical asymptote looks like. Slant asymptotes are also called oblique asymptotes, right? So one of those things that you need to know the different names of. With a rational function, you are not going to have a horizontal and a slant in the same function because they're both talking about in behavior at the infinities, and that you can't have two different conflicting things there. But you could have a vertical and a horizontal, or a vertical and a slant. Okay, those things can go together. All right, so let's do this. Most of what we do today will be a review. Talked about all of these things, got talked about in Algebra 2, some more than others, but this is going on page 61 when we're done. Okay, so rational functions have restricted domains leading to discontinuities in the on the graph. So your rational, like your R of x, always has x's in, at least in the denominator. It may have just a constant in the numerator, but it's two different functions being divided. All right, so back up here. Our types of discontinuities. We got vertical asymptotes, horizontal asymptotes, slant asymptotes, which slant could also be called what? Oblique. Oblique. Thank you. Okay. Slant and oblique. In your oblique muscles, what do they allow you to do?
Rotate, slant.
Lean over. Like these are your obliques, right? So you get to slant like that. Okay. And point discontinuities, this can also be called removable. Okay, and we are going to start with the point discontinuity, or removable. We talked about them in both ways. We are going to abbreviate that as PD for point discontinuities, so we don't have to write that out all the time. Or holes, that means I'm going to have a hole in my graph. Okay, point discontinuity or holes in the graph occur, so holes occur when a factor containing x is common to the numerator and denominator. Okay, so if you have a factor that's common to the numerator and denominator, that's where your hole is going to appear. So on all of these, we need to start by factoring. Okay, so what can I factor the denominator? What can I factor out down here? 3, oh, that's a 2. Okay. 3x times x minus 2, right? And then it's x squared in the numerator. I'm going to write it as x times x, though, even though I know even when you factor, you're not going to do that. And I don't expect you to do that. I just want to make sure that I don't lose anybody here. So I have this x and this that are common in the numerator and denominator, right? So since that happens, that means I know before I go any farther, since there's an x in the denominator, that tells me that x cannot equal 0, right? And that's an important thing for us. And then these right here, they're out, right? So that means my function in the end, once I cancel that out, is going to be x over 3 times x minus 2. My point discontinuity that I'm going to have has an x value. This is the x value of my point discontinuity because there's going to be a hole there. X can't equal 0, right? And then I got to figure out what the y value is. So in order to do that, I have to find f of 0. So it's going to give me 0 over 3 times 0 minus 2. So what does that give me? 0, which means I'm going to have a hole here at 0, 0. So here's my function. Here's my point continuity. And so what all this tells me is that the graph looks like this with hole at this point right here. Okay, so this is what my graph will actually look like, but I got to make sure I have a hole in my graph at 0, 0. Okay, everybody okay with that? Easy enough? All right, good deal. So let's look at number 2. If I factor number 2, the numerator is going to give me, let's see, this is going to be x and x. This is going to be, signs are different, so it's x plus what and minus what? Minus 3 and plus 2. And then the denominator can be x plus 3 times x minus 3, right? So these are going to cancel out right here. And then what that tells me is that x minus 3, I cannot forget that this was ever there. Even though I'm going to cancel out, I'm not going to use it, I know that x minus 3 can't equal 0 because that was actually there in the denominator, which means x cannot equal 3, right? And so this is the part I'm going to use in my point discontinuity. Once I cancel those out, my function is x plus 2 over x plus 3. My point discontinuity, the x value is what? 3. And then I have to find f of 3, which is going to be 3 plus 2 over 3 plus 3. What does that give me? 5/6. So that is my point. This is my point discontinuity. This is my reduced function. Everybody okay with that? Any questions? All right, you work on number 3. Okay, so when I cancel that out, I get to cancel out the whole 2x, like the numbers get canceled out as well. When I get this right here, when I graph this, just this thing right here, what's it going to look like?
It's a linear function.
It's a linear function. It's going to be a line, right? But it's not just any old line. It's a line that has a hole at 0, what? Negative 3. Okay. So at first glance, when you look at that function, the way it's given to you totally does not look like any line you've seen, right? But when you reduce things out, it's going to end up graphing as a line. You just have to pay attention to that hole there. So before you start canceling things out, remember it still tells you something. You've got to do something with it before it's just completely gone and you forget that it ever existed. Okay, we all good? Yes? All right, so there are your point discontinuities. Now, vertical asymptotes, which I know you already basically understand because we had to talk about them on Friday and that was no big stretch for you. So vertical asymptotes occur when a factor containing x is unique to the denominator. Unique to the denominator. Doesn't just mean that I have something in the denominator. So when I look at number 1, here, can I factor this at all? Can I reduce it at all? No, so it is what it is. So at this point, x, this is a factor, x plus 2, it's unique to the denominator. So we know that x plus 2 cannot equal 0. So that means x cannot equal negative 2. Therefore, I have a vertical asymptote at what? What's my vertical? X equals negative 2. Since x cannot equal negative 2, this is my vertical asymptote here because it'll never touch that. Okay. Everybody good with that? Any questions? All right. So then let's look at number 2. Can I factor number 2? Yes, this is going to become x plus 7 times x minus 7 over x minus 7. So can I reduce things here? Yes, these can cancel out. But remember, I have to pay attention to the fact that x minus, or x, I just can say x cannot equal 7. I think you know where that comes from now. You don't necessarily have to write x minus 7 equals 0. But x cannot equal 7. So my function then is giving me x plus 7 vertical asymptotes. There's none. Is there a factor that is unique to the denominator? No. Well, 1, but it doesn't contain x. Okay, that's why I have to say containing x, so you're right. That's still not unique to the denominator, though, because technically it's in the numerator. But yes, this was in the denominator, but it's not unique to it because it was in the numerator also. So there are no vertical asymptotes, but I do have point discontinuity, right? What's the x value for that? 7. So what's the y value? 14. My discontinuities. Okay. Everybody good so far? Yeah? All right. So you do number 3. So I end up with 2 different things here. X can't equal 4 and it also can't equal negative 4, but they tell me different things, right? When x can't equal 4, what am I going to have there? A whole. That's the x value for my point discontinuity, right? And then when it can't equal negative 4, that one right there is unique to the denominator. That means my vertical asymptote is x equals negative 4. So f of 4 is equal to 2 over 8. What does that become? 1/4. Here are my discontinuities. Okay, everybody okay with that? Any questions at all? All right. There we go. So here, this is already factored for me. Can I reduce anything out? No, sure can't. So here, x equals 0, and this means x plus 5 cannot equal 0. So that means x cannot equal negative 5. Do I have any holes in this one? No, but I have 2 vertical asymptotes, right? One at x equals 0 and one at x equals negative 5. Any questions at all about that? We're all good? Sweet. All right, so then we're going to talk about horizontal asymptotes. When you look for the horizontal asymptotes, you are looking at the rational functions to see if they are top-heavy, bottom-heavy, or tied in degree, right, as far as the degree of the function. So it says horizontal asymptotes occur when the degree of the denominator is greater than or equal to the degree of the numerator. So we've got top-heavy, bottom-heavy, and tied in degree. So top-heavy, starting here. Greater in degree in the numerator would indicate no horizontal asymptote. So if you look at this right here, we have degree 2 in the numerator over degree 1 in the numerator. So that would be top-heavy, right? The numerator's degree is higher than the denominator degree. Can I factor this numerator here? Is there a GCF in the numerator? 2, right? So I can factor out the 2, and that leaves me with x squared plus 2x minus 6 over, minus 3, dang it, thank you. Minus 3 over x plus 3. Can I factor that some more? Yes, this factors into x plus 3 times x minus 1, right? All over x plus 3. Can I reduce this? Yes. So that cancels out. So f of x is just equal to 2 times x minus 1. Is it still top heavy? Yeah, because the degree of the numerator is now 1 and the degree of the denominator is now 0. So if what you look at before it gets reduced is top heavy or bottom heavy or tied, if you can then cancel something out, is the fact that it's top heavy, bottom heavy, or tied going to change? No, because you just changed the numerator and the denominator by the same degree. Does that make sense? So if all we cared about was the horizontal asymptote, reducing the function out it doesn't even matter to us. But what this tells us now is that our horizontal asymptote, because it was top heavy and it still is top heavy, is none. What do I have though? A hole. I have point discontinuity. My x value is -3. What would the y value be? You'd have -3 minus 1 is -4 times 2 is -8. Okay. But I wanted you to see that when you have that top heaviness, bottom heaviness, whatever, even if you reduce something out, the top heavy or bottom heavy part of that doesn't change because you're reducing it, because you're canceling something out of both. All right, so let's look at number 2. Top heavy, bottom heavy, we're tied in. What is this? It's top heavy, right? So what does that tell me about the horizontal asymptote? None. It's that easy. If it is bottom heavy in degree, so the greater degree in the denominator, asymptote, so 0 over degree 1, right? So bottom heavy, which means you have a horizontal asymptote where y equals 0. This is degree 1 over degree 2. So what's your horizontal asymptote? Y equals 0. It's that easy. Bottom heavy, y equals 0. Okay. Everybody okay with that? So top heavy, there is none. Bottom heavy, it's y equals 0. If they are tied in degree, so this is degree 1 over degree 1, then it leads to a horizontal asymptote where y equals the ratio of the lead coefficients of the numerator and denominator. Lead coefficient is 2 and 5, so that means my horizontal asymptote is that y equals what? 2/5. That's it. Okay, y equals 2/5. So here this gives me degree 2 over degree 2. Therefore, they are tied. So my horizontal asymptote, that's 2 over 2, which is 1. And that's it. Okay, everybody okay with that? Any questions at all? All right, so then we have our slant asymptotes. What's another word for slant asymptote? Oblique. Oh, not with 2 E's. There you go, oblique. Okay, oblique or slant asymptotes. Those occur when the reduced rational function contains an x in the denominator and the numerator is 1 greater in degree than the denominator. Reduced, okay? And it says when x is in the denominator and the numerator is 1 greater in the degree than the denominator. That means it's top heavy. When it's top heavy, what's happening with your horizontal asymptotes? There's none. If it's top heavy, there's none, right? So you can look at all these and you're like, yep, no horizontal asymptotes, and you're not, because you're never going to have horizontal and slant at the same time. So no horizontal, but there is a possibility there could be a slant asymptote, and it does say reduced, so I have to actually figure out what all is going on here. So I'm going to try and factor the numerator here. Does the numerator factor? Yes. What do I get in the numerator when I factor it? -3 and -3. 1. So I factored it. Nothing cancels out. So do I have any holes here? No, I do not. Okay, so this is my reduced form because I can't reduce it. It is, there's an x in the denominator, and the numerator is 1 greater in degree, which means I'm going to have a slant asymptote. Then it says you find it by dividing the numerator and the denominator. So we have options of how to divide this, right? Synthetic division or long division. What would you choose here? Synthetic, because I can do synthetic with this one, right? So on the outside, what goes on the outside? 2. Okay, so on the inside, I ignore the factored form. I actually need this form for the inside. That's going to give me 1, -4, and 3. So I bring down my 1. It's 2, -2, -4, -1. So my slant asymptote is at y equals, what does this give me? X minus 2. And then, do I care about this? Do you remember? We don't even care. Okay? Next time we talk, and I would say tomorrow, but tomorrow we're reviewing, so whenever the next set of notes is, which I guess is Thursday, we are going to look at why we don't care and what the remainder actually tells me. Do you know what the remainder tells you? So I'm guessing you probably, what did I say, the remainder? The remainder, it tells you something, but we don't use it here. There is a purpose, and there's a reason that we just ignore it, okay? And you will never get 0 there. If you got 0 there, then something should have canceled out, right? Because if I can divide it out completely, that means that they're the same, and I could just cross things out. So you just ignore the remainder. This is where your slant asymptote is. It's a line that should be no big surprise, right? And you just ignore the remainder. Okay, we all good with that? Because there's a visual that goes with that. This will be way better than me just trying to explain it or draw it for you at this point. Okay, so then we move on to number 2. So I'm going to factor this. So I'm going to get 2x times x minus 2 over 2x. So can I cancel this out? Yes. So I'm left with f of x equals x minus 2. So, do I have a slant asymptote? No. This is my reduced function. There is not an x in the denominator, because when I graph this, it's going to be a line. So there is none. Do I have any discontinuities? A whole. I have a point discontinuity. What's the x value for that? You look back over here, right? Remember that x cannot equal 0. So it's at 0, -2. Why is it what? Why is there none? Because once I get here, this is my reduced, right? There is no x in the denominator. So the numerator is 1 higher in degree, because the numerator would be degree 1, the denominator would be degree 0, but degree 0 we don't count, okay? So there's just none here. Might look like there should be one at the beginning, because we knew at the beginning just by glancing at that, there's no horizontal. So there's a possibility there's slant, but we're not guaranteed depending on what happens, okay? We all good with that? Any questions at all? Awesome. All right, you work on number 3. Actually, we'll do number 3 together. Even if I could factor the numerator, when you look at that, no matter what I factored that into, would I be able to cancel the x out of the denominator? I mean, we should know enough about factoring that it would factor into 2 binomials if it factored, and that's not going to help me, so it doesn't even matter at this point. So this is it, right? Which means I'm going to divide. Can I use synthetic division here? No, because this coefficient would have to be 1, and it's not. So instead, I'm going to have to do long division. So 2x divides into 2x squared minus 4x plus 3. So 2x goes into 2x squared. X times 2x is 2x squared. Subtract that out, and then I bring down my -4x. Oh, that's a 48, my lord. Okay. 4x, 0 there. So 2x goes into -4x minus 2 times. So this is -4x, and then that gives me 0, and I bring down my 3, which means I'm going to have a remainder. Do I care about the remainder? No, at this point I do not. So my slant asymptote then is at y equals what? X minus 2. And notice here, if I had done long division here, I would have gotten x minus 2 and I would not have had a remainder. That's because it completely cancels out. So you will expect a remainder when you're doing slant asymptotes every time. If you don't get one, then you missed something that you were supposed to cancel out. Okay, we good? Questions? All right, you work on number 4. Don't waste your time factoring because you're not going to be able to cancel things out there. You gotta change the signs. I wrote the wrong thing down the first time.
Oh, yeah.
Yeah. Yeah, so if you were just copying me down, I wrote the wrong thing down the first time. All right, so this is what I get. This is my remainder. Don't care. Right? My slant asymptote is y equals 2x minus 8. And do you think you'll get a line every single time? What guarantees you that you'll get a line every single time? This is slant. Well, what has to be true about the degree of the numerator and denominator to have one? What's part of the rule there? The numerator has to be how many bigger? 1 degree bigger. So if it's 1 degree bigger, when I divide it out, aren't I always just going to have a single one left? Like if this, every time you'll have x to the first. And I went back just one step here. I want you to look at number 3. Okay, so 2, 3, and 4 all have some things in common. I mean, these two had the same denominator, but they acted differently, right? And this was something that I was going to have to divide. I used long division here. But if you have a monomial, for a monomial, I'm not worried about even showing you this little shortcut here, but a monomial, then you can do a short division type of thing, meaning that when you do all of this, like the long division, if you just ignore that because that's where your remainder is going to come from. If I do this if I do 2x squared divided by 2x, that just leaves me with x, right? If I do negative 4x divided by 2x, that leaves me with minus 2. And then that's a remainder and I don't care about. So you can kind of just reduce it that way and you get the same answer. So if you understand how to do that and you can do that accurately, then you're good. Okay? Questions? All right, grab your homework. What'd you say? Only with a monomial, yes. On your assignment, I tried to give you enough room right here to work with these questions. Hopefully that, I mean, if you need an extra sheet of paper, you shouldn't for like every single question. When you put these in here, if there isn't one, you need to put none. Leaving it blank tells me you don't know the answer to the question, okay? So if there's none, make sure you write none. That will be the answer for quite a few, depending on what you're doing. On the back, it says to sketch. I do not expect you to sketch the entire graph necessarily. What I want you to sketch back here are the discontinuities. If you have asymptotes, graph them. That's all that has to be back here. If there's a hole, graph where the hole would be. So you would write down what you have, like vertical asymptote here, but you don't have to write down the nones. Basically on the back, just write down what you do have and graph that. If you feel like you can graph some more of the graph and you want to, that's fine, but all you have to have on the back are the discontinuities. Does that make sense to you? We good? Because we haven't talked about the other graphs yet. All right, awesome. So you got lots of time left to make a good use of that time and work.